Hello, 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 hello.
Hello. Hello, everyone. Welcome back to the afternoon session. So, our first talk will be by Soumyajit Pyne. His talk will be on cooperating principles can extract full welfare in optimal contracts.
Thanks, Shom, for the introduction. So this is a joint work with Umang and Raghu. So let's start with an example. Uh, Suppose there is a woman and we call this woman the principal, and there is a security agent or the agent, and she wants to hire someone from him. And so there are two actions of this security agent, which is like he can be lazy in the work or he can be alert. Okay. And based on that, two things can happen. There can either be a security breach or not. Okay. So let's see it through a mathematical model. So this agent has two actions, being lazy or being alert. And based on that, the principal can see two outcomes or observe two outcomes, breach or a no breach instance. So each action is, has a cost. So being lazy is like super easy, but being alert, it is a little bit difficult. So there is a cost associated with it. Now, if the agent take the action lazy, then there is a 2/3 probability of a breach, security breach happening, and a 1/3 probability of a no breach instance. Similarly, if he chooses the alert action, then the probability of breach reduces and the probability of no breach increases. Okay. Now the thing is that the principal can only see the outcomes. It cannot, she cannot see what action this agent is speaking, because she cannot monitor the security guard all the time. Okay. So, okay, so now let's do some mathematical stuffs on this matrix. So what is the expected reward from this lazy action? Okay, by the way, I missed one thing. So this, the principal has a reward of 0 for the outcome breach and a reward of 1 for the outcome no breach. Okay. So what is the expected reward of this action? It's basically 2/3 into 0, 1/3 into 1, which is 1/3. Similarly, what is the expected reward for the action alert is 1/3 into 0, 2/3 into 1, which is 2/3. So this action has a higher expected reward. Okay. But as I already said, the principal cannot observe the action taken by the security. Then how the principal would pay the security? She can only pay depending on the observed outcome. Like she can only say, okay, if there is a breach, I'll pay, I pay nothing. If there is no breach, I'll pay you this. So let's see an example. And this payment scheme is basically, we call a contract. So yeah. Agent's cost, meaning that, okay, let me, okay, so the the agent can take two actions. So being lazy is easy. So 0 means that this action is like easy to take, or this action has a lower reward for the principal. But this action has a higher reward for the principal. But to take this action, this is like a little bit difficult for the agent. So it has a cost associated with it. Okay. Great. There is only one player here in our model. This is only one agent and one principal. That's it for this scenario, at least. Okay. So let's say the principal says, okay, I'll pay nothing for both of the outcomes. So basically, we write it as this 0, 0. So 0 means this 0 means the principal is paying 0 for this outcome, and this 0 means the principal is paying 0 for this outcome. Then what is the expected payment for the action, the lazy action? It's basically 0. 2/3 into 0, 1/3 into 0, which is 0. And also for the alert action, it's 0. So basically the principal is paying nothing for this payment scheme. Now, what is the utility of the agent based on this payment? So the utility of the agent is for the action lazy is how much the expected payment from the principal for this action, which is this, minus the cost, and which is 0 for lazy, and which is 0 minus 1 by 18, which is minus 1 by 18 for alert. So then which action the agent would pick? Sorry, the agent would pick this action because this has a higher reward for the agent. So yeah, so the agent would pick the lazy action. As soon as the agent picks the lazy action, what is the principal's utility? Principal's utility is what is the reward for this action minus how much the principal promised that I would pay for this action. So it's so it is 1/3 minus 0 because the contract is 0. So 1/3 minus 0, which is 1/3. Okay. Any questions here? Then we'll see one more contract. Okay. Let's see one more contract for clarity. Let's say the principal says, okay, I'll pay 0.5. Okay. Yes, exactly. Just how much I'm paying for this, how much I'm paying for this. That's it. Okay. And we say it by T. Okay. Describe it by T. Okay. So if the, now focus on this contract, then what is the agent's utility for this action lazy? It's basically 1/3 into half, which is 1/6. Because for this outcome, the principal is paying 0. So we'll just focus on this column. So for lazy, the utility of the agent is 1/3 into half minus 0, the cost is 1/6. And for alert action is 2/3 into half minus the cost, which is 1 by 18. So it's 5 by 18, and you can check that 5 by 18 is bigger than 1 by 6. So the agent would choose the alert action because it has a higher utility. Then what is the principal's reward from this contract? Is as the agent is choosing the alert action, then the expected reward for this action alert minus how much the principal has promised to pay, which is 2/3 into 1 minus half, which is 1/3. So this contract is not good enough because the previous contract where you were paying nothing, still you are getting a utility of 1/3. The principal was getting a utility of 1/3. Here also she's getting a utility of 1/3. But the main difference is that the previous contract was incentivizing the lazy action, and here the contract is incentivizing the alert action. So can we do better? And yes, we can do better. Focus on this contract, 0.1 by 6. And you can just calculate that agent's utility will have a tie for both of this action on this contract, 1 by 18 for both. And there is an assumption that the agent resolves the tie in favor of the principal. So then the agent would choose the higher reward action, which is alert. And the principal's reward will be like 2/3 into 1, the reward, minus how much he's paying, which is 1 by 6, which is 5 by 9, which is bigger than 1/3. So now this contract is better than the previous ones. Okay. So now let's formalize it with some notations. We have n actions, m outcomes. Here n and m both are 2 in on those examples. There is each action has a probability distributions over the outcomes and a cost, non-negative cost. And also each outcome has a reward. So like in the previous case, we had reward 0 and 1. So it is basically a non-negative m-dimensional vector. And contract is also a non-negative m-dimensional vector. Note that we can't pay negative. The contract should be non-negative. Okay, great. Now, so these are just the terms that I have already said in a formal notation. Basically, if you are given a contract T, the agent always chooses the action which maximizes its utility, basically the expected payment for that action minus the cost, and which action actually maximizes this quantity, the agent would pick that action. Similarly, the principal's reward is the expected reward from that action minus the payment that the principal has promised for that action. Okay. Now, these are so a social welfare of an action, we define it by the principal's utility plus the agent's utility. Basically, you just add these two things, and you can see this T is gone from the sum. So the social welfare of an action does not depend on the contract. It just depends on the matrix. Okay, and it is basically the expected reward of that action minus the cost. T was the contract. Okay, great. So yeah. The whole matrix is the input. Yeah, we have to just compute the T. Okay. So that was the social welfare of an action, and the social welfare of an instance. Instance means the matrix is basically the max of all the social welfares. Okay, great. So now what is our goal? Goal is to choose a contract that maximizes the principal's utility, and we call it as the optimal contract. Okay. So we have one more assumption, which is like there always exists a zero cost action. That means the agent's utility cannot be negative, because there is always a zero cost action. If for some contract the agent's utility is negative for all the other actions, the agent can always choose that no cost action, the zero cost action. That means, so remember that social welfare was principal's utility plus agent's utility, and we know that agent's utility is always non-negative. That means the optimal value is always upper bounded by the social welfare. Okay, optimal value means the principal's utility, and this value can be computed polytime in polytime. So basically, you can compute a contract poly in n, m, and the input size. Any questions up to this point? Yeah. The whole matrix is given to the principal. Okay. Any questions up to this point? Okay, great. So, okay, now let's talk about some related words. So, contract theory is basically lies in the intersection of economics and algorithmic game theory, and also Hart and Holmstrom got the Nobel Prize in economics in 2016 for contract theory. So there are some variations of this model. One model is that the principal is uncertain about the whole matrix. Okay, so like the principal does not know all the actions. Okay, it can happen in real life. Also, there are things like simple contracts. So maybe the optimal contract that you generate from a matrix is very hard to say to a person. So like, let's say I'll pay you for 0.3245 for breach. It is not simple. So people also study simple contracts. One of such an example is linear contract, which has amazing results in some different variants. Also, there are variants with multiple agents. So like Nilhara has said, so if you have multiple players, then what can happen? And also Swaprabhu has said some kind of when you have multiple agents, you talk about this coalitions thing, like there is a subset of players and what is the worth of that? It's basically something like that. You have like multiple players and the incident can happen or not. And that has some probability. So it is something like that. But what are we interested in this talk is basically multiple principles. Okay. So let's talk about this. Now let's say there are two principles, and these are the same matrix, but actually I changed the second action. Previously it was 2/3 and 1/3, but I've changed this to half and half because of some mathematical reason. But both of the principal has the same instance. Okay. So if they individually contract with the agent, the security agent, you can compute the optimal contract is 0,1/3. You can just check offline, and the incentivized action will be this action, and the principal's utility will be 1/3. So that means if they go individually to the security agent and they contract, they cannot get more than 2/3, right? Now, what can happen if they cooperate? Okay. So how do we define the cooperating setting? Let's see. So this is the single instance and this is the cooperating instance. So let's think about this. If the two principals jointly go to the security agent, then what actions are possible? The security agent can be lazy for both, can lazy for one of them, can be alert for both of them. So 1-1 means lazy for both, 1-2 means 1-2 and 2-1 means lazy for one of them, and 2-2 means alert for all of them. Also, what could be the outcomes? Breach for both of them, breach for one of them, or no breach for both of them, which is basically 1-1, 1-2, 2-1, and 2-2. That's it. And these probability values are basically the product distribution of these actions. So basically 1-1, so the entry for 1-1 is basically the product distribution of 2/3 and 1/3 jointly. Okay, and you can just check this matrix. So one thing I want to note is the cost is additive. That means the cost for this action 2, 1 is basically the cost for action 2 plus the cost for action 1. This is 1/18 and 2, 2 is 1/9. Similarly, the rewards are also additive. So for both of them with no breach, the reward is 2. One of them with breach is 1/1, and both breach is 0. Security breach. Yeah. I mean, we introduced this model. There can be such models. I mean, if you define it that way. We just worked with this model. Yeah. Suppose. Yeah, I mean, so the security agent, you can think it's a farm and it sends people who works for you. Now, let's say, so I send 2 people for 2 of the principals, but now I can send lazy people for both of you, alert people for both of you, or one of them I can say send lazy people. Or you can think it in this way, it's a different example. So let's say let's say ID Bomb and TIFR. No, you can also, yeah, you can also think it this in this cloud service way. So let's say TIFR also take a cloud service from Amazon, and ID Bombay also takes cloud service from Amazon, and they have single contracts, individual contracts. Now let's say they cooperate, they go to Amazon and they give a joint contract. Okay, for both IIT Bombay and TIFR, can they do better? That's the question. So yeah, any questions? Yeah, we can have. And cooperation is better, we'll show that. So yeah, 5 minutes. Oh, okay. Okay, so I'll just go fast because I have only 5 minutes. I mean, right? So let's see. So observe this contract. What this contract means is both the principal goes to the agent and it's saying that so we'll pay 4/5 only if there is no breach for both of us. For that contract, you can check that the principal's utility is 4/5. Okay, you can check, and which is bigger than 2/3. Previously, when they're separate, they couldn't do better than 2/3. But when they jointly offer a contract, they can do better. No, this is the joint interest. So both of them are together, they are getting 4/5. How they separate this reward, that we don't say here, but their joint reward is 4/5. But previously, both of them, each of them was getting 1/3. Rewards are additive. No, the total reward is 4/5. No. So the total reward is I mean, there is a contract here, which is this, and this contract has a reward of 4/5 for total. I mean, both of the principals. No. So are you saying that both of them are getting 2/5, 2/5, something like? Yeah. So twice of 1/3 is 2/3. Yeah. Yeah. Okay, great. So yeah, so you can do better. And we can prove that cooperation is actually better. So if you cooperate, you can always do better than single instances. And there is a simple fact that the social welfare is additive. Okay, so basically the social welfare of the joint instance is basically sum of the social welfare of the single instances. Okay, so the thing is that by cooperation, how much we can do better. So this is the theorem. So we have n actions, and let's focus on an instance I and focus on this term 2 into OPTI. What is 2 into OPTI? This is the principal's reward for each of the instance, and there are two principals. So then in the single instance, their utility will be 2 into OPT. And see this thing, this is basically the joint instance. So we proved that there exists an instance where you can do almost n times better than single instances. Okay, which is huge. But note that this is a worst case result. I mean, there exists an instance where you can do like n times better with only two principles. So what about general case? So for the general case, we need some prerequisite, which is like, suppose there are t instances I1 to IT, and there are k principles from each of the instances. Okay, then how many principles are there? K into t, right? Then the joint instance, we can write it like this. So take the tensor product of all of them and then repeat it k times, because there are like k copies of principles from each of the instances. So you can think it as a joint instance or joint matrix of those k into t principles. Recall that social welfare is additive, and also social welfare is an upper bound on the optimal cost. So then the optimal for the joint case is upper bounded by the social welfare of that case, and by this additive property you can just write the social welfare of this joint instance as this k into sum of the each thing. Okay, just forget everything, just focus on this part. Okay, this is an upper bound on the optimal reward. Now this is the last theorem, is that what can we say about the general case? Suppose we have like t instances, and for large enough k, there are like k principles from each of the instances. Then the optimal reward from the joint instance is at least the social welfare of that instance into some multiplicative term which is less than 1. Now note that this thing is upper bounded by this term, which comes here. And there is a multiplicative term which goes to 1 as k tends to infinity. That means in the limit, the principles can extract the whole social welfare. If k tends to infinity, they can get the whole social welfare, and the agent, recall that the social welfare is principal's utility plus the agent's utility, and the principal is extracting the whole social welfare. That means the agent can do no profit in the limit. Okay, so we had more results on the different topics in our paper, but this was one of the main results, that no matter what is the instance, if you cooperate, you can extract the entire social welfare. Okay, and what are some open questions? Also, I'll end with some open questions. So we saw cooperation in this model. How can we define competition in this model, and can we contrast them? And we can also think of a scenario where the agent cannot take all the actions. Maybe the agent has a budget, and it cannot be alert for both of them. Let's say they have a budget, so that action is not feasible for it. Then what can we say? And also, so this instance is exponential in k, because each time you do a tensor product, the number of actions grows exponentially. So previously the action was n, now it's n square and it's n cube. So can we compute? So for a single instance, we can compute it in poly n and m, but now the n and m is exponential in k, the number of principles. Can we do it efficiently? So these are some open questions, and yeah, thank you. Yes. Yeah. So
Any fairness ideas?
Yeah. So actually, there is one part of our paper which gives the agent also a power. So like the agent can add one more action. There is only one principle, but the agent is allowed to add one action that the principal does not know. The agent will add. Then how much the agent can hurt the principal, that we also have analyzed in our paper. But in this instance, we don't give the agent power as such.
And the other question is, how critical is it? How much is it dependent on this additivity assumption? Your
additivity of what?
Your utilities are additive. The rewards are additive.
Okay.
Is that critical? So, for instance, if I want to extend it for
because
submodular, Yeah, so
Yeah,
supermodular.
that's a great question. So like the cost could be submodular. So like if you're taking the allied action for both of them, maybe it's submodular. It's not just
Oh,
additive.
so I'm not talking about the agent side. Of course, agent could be additive, but from the reward side,
reward also.
I mean, both sides you can think of this. So
The submodular thing. Yeah, we haven't thought about that actually, but that's a nice question. We can, but in the proof, we need this additivity because we use social welfare in our bound in lot of the time, and we use this fact that the social welfare is
Yeah, that's
additive. Social welfare is only additive if this is a tensor product. Otherwise, maybe you can show that it's not additive. So we need these bounds and all. Yeah. Any other questions? Okay.
So our next speaker is Yeshwant.
इसको पॉकेट में डाल